Today we're taking a look at limits, and we've actually seen the concept of a limit before in advanced functions, and where you would have seen it in advanced functions is when we're dealing with asymptotes, when we're looking at that end behavior, and when we are dealing with tangent lines. Okay, so we're going to do an investigation to start off with. So let's take a look at this function f of x, and the first thing that I notice here is that I can simplify this function by dividing the factor x plus 3. And so this is 2 bracket x minus 2, but x cannot be equal to negative 3. So let's just go ahead and write down our domain here. So our domain for this function f of x is x such that x cannot be equal to negative 3 and x exists as a real number. What happens at x equal to negative 3? Well, there's a hole. So we have a hole at x equals negative 3, and we can find out exactly where that hole is by plugging negative 3 into our function. So f at negative 3 is equal to 2 bracket negative 3 minus 2, which is equal to 2 times negative 5, which is negative 10. So this is where our hole is, okay, at negative 3, negative 10. So let's go ahead and we're going to graph this function. So let's take a look at our graph over here. I'm just going to set up with my scale. So I'm going to have these ones go up by 1. I want to be able to show this hole, which has a y value of negative 10. So I'm going to go on my y-axis by 2. Okay, and we're just graphing the line. If you wanted to simplify this, this is, f of x is equal to 2x minus 4, so a y-intercept of negative 4 and a slope of 2. I'm going to add my hole first, though, which is at negative 3, negative 10. So that is right here. And then my line, again, has a y-intercept of negative 4 and a slope of 2. So I'm going to now add the pieces of my line. Okay, and there we go. There's our function f of x. And so now we're going to talk about what a limit is. All right. Okay, in advanced functions, MHF, 4UO, we had notation when we talked about end behaviors and behavior next to asymptotes. So we would write something like, as x approaches negative 3 from the left, we would take a look and see what our function approaches. And on this graph, when I approach negative 3 from the left, I'm looking at over here, my function is approaching the y value negative 10. And as x approaches negative 3 from the right, my function is approaching, again, that y value of negative 10. So this is actually a limit. Okay, we write it a little bit different. So we use limit notation. And I'm going to go over that right now. But it's basically kind of describing the same thing. So we would say the limit of this function as x approaches, so we write it underneath, negative 3 from the left of our function f of x is equal to negative 10. So again, just to go over that, the limit as x approaches negative 3 from the left, so we're kind of, recreating this here, of that function is negative 10. Okay. Then the limit as x approaches negative 3 from the right for this function f of x is equal to negative 10. So if these actually both are the same, if our limit from the left is equal to the limit from the right, then that limit exists and it is equal to negative 10. So we would then conclude that the limit as x approaches negative 3, so from the left and the right, for that function f of x is equal to negative 10. So that would be our conclusion. So let's define this more generally now. So the limit as x approaches a for a function exists if, okay, number one, if the limit as x approaches a from the left of that function exists, okay, so it has to exist. And number two, the limit as x approaches a from the right also has to exist. And number three, the limit as x approaches a from the left of that function, f of x, equals the limit as x approaches a from the right of that function. So if all of those three things, they must all be true, then the limit exists. Okay? And we have a limit. So these must all be true. And if they're not, then the limit as x approaches a for that function does not exist. Okay? So again, we're looking for all these three things to be true. So let's take a look at an example. So here's a function that's given. First of all, we're going to answer question A, is f of x a function? And we can see that it passes the vertical line test. Yes, it is a function because every x value has only one y value. And again, you can use your vertical line test to test that. When I look at evaluating my function at 1, I can see this is where my function exists at 1, so the y value there is 0. Now we're going to go ahead and find the limit as x approaches 1. Okay, so the limit as x approaches 1 from the left of our function. So I take a look at it as it approaches 1 from the left, I'm approaching the y value of 0. Then I'm going to find the limit as x approaches 1 from the right for my function. And approaching from the right, my function is approaching the y value of 1. Okay? So then we would say since the limit as x approaches 1 from the left of the function does not equal to the limit as x approaches 1 from the right of that function, the limit as x approaches 1 of that function does not exist. Okay, so that is our kind of intro into these limits. Now we're going to talk about continuity, okay, and what makes a function continuous at a certain point or an entire function continuous. And there is a relationship between limits and continuity, and you'll see that in a minute. We're going to first define 3 different types of discontinuity, okay? So I'm going to draw a little picture the best that I can. First, I'm going to draw a set of axes. So jump discontinuity would have, like, let's say, I'm just going to label an x value here. Let's say we have our function going like this and like this. So kind of like our last example, we would call this a jump discontinuity. So, we go from a y value here and we jump up and continue on with our function up here. Okay, so this one is discontinuous at x is equal to -1, and that's a jump discontinuity. So now let's take a look at a removable discontinuity. So a removable discontinuity would look like this. I would have a hole in my function. So this one is discontinuous at x equals 1. Okay, hopefully you can see the difference between a jump discontinuity and a removable discontinuity. And lastly, we have our infinite discontinuity. And this one you would have seen in advanced functions when you were graphing your rational functions. So these are asymptotes. Let's say my function goes like this. And let's say that asymptote is at x is equal to 2. So my function doesn't exist at x equals 2. We would say this is discontinuous at x equals 2. Okay, so what I want you to do now is just pause the video, and I want you to answer what's in the boxes here for each of these graphs that I've put. So I want you to say whether this function is continuous, what type of discontinuity there is, and then evaluate the limit at an x value and evaluate the function at that x value. Okay, so pause the video and go ahead and investigate these 4 functions. Okay, so let's take this up. So this function is not continuous. And remember, for a continuous function, we can basically keep our pen on the paper and continue to trace across that function without any breaks. Okay, and the type of discontinuity this is a jump discontinuity. When I evaluate the limit as x approaches -2, because the limit from the left doesn't match the limit from the right, this limit does not exist. My function at -2 has a y value of 1. Okay, for my second one over here, is this a continuous function? No, because I have a hole in the graph here. So this is a removable discontinuity. When I take a look at the limit as x approaches -2, because it approaches the same y value from the left and the right, we do have a limit here, and that limit is -2. And when I evaluate this function at -2, it does not exist. Okay, for our next one, is this a continuous function? No. The type of discontinuity, I would accept actually either a jump or removable. Okay. When I take a look at the limit as x approaches -2, approaching from the left and the right, it's the same. When I evaluate my function at -2, it evaluates at 3. This last one is a continuous function. There is no discontinuity here. The limit as x approaches -2, again, is the same from the left and the right, it equals 1, and my function at -2 is also equal to 1. So I want you to kind of think about the relationship between these discontinuities and whether or not this function is continuous. So we can see in these examples, hang on a minute. So this one is not continuous, not continuous, not continuous. This one is continuous, okay? And I want you to pay attention in particular to the fact that my limit at a particular point was equal to my function evaluated at that same x value, okay? And that's what we're getting at in terms of seeing that connection between a continuous function and not having a discontinuity and using these properties to show that a function is continuous. That's what we're getting at right here, okay? Oops. All right. So let's just go ahead and kind of summarize what I just was trying to highlight. So when we looked at the function, the limit as x approaches -2 for that function, it existed. We also found that f at -2 existed. And in that last function, we had the limit as x approaches -2 of that function equal to our function evaluated at -2, okay? And basically, that's what we need to happen to show that a function is continuous at that point. Okay, so we're going to formally write down the definitions. So basically, we're going to take what we just wrote down with that example and then generalize it. So when we're looking at continuity at a point, okay, and in the last example, we did at when x is equal to -2, f at x is continuous at x equals a, okay, if the following conditions are satisfied. And as I mentioned before, there's three things. So one, the limit as x approaches a for our function f at x exists. Two, the function at a must exist. Okay, so there's not a hole or anything like that. And three, that limit as x approaches a of our function is equal to our function evaluated at a. Okay, so if any of these conditions are not met, then we would say that f at x is discontinuous at x equals a. Now, when we're talking just in general about a function, we consider a continuous function. A function is continuous if it is continuous for all values of a, okay, or all values of x, okay, where x is a real number. So a function is continuous if it is continuous for all x values when x is a real number, okay? If a function is not continuous for any x, then our function f at x is a discontinuous function. Okay, so we're going to take a look at our last example here. We have a piecewise function. We're going to start by graphing this function. Okay, so we have a cubic function shifted down 1, and then we have f at x equals to 2 for all values of x greater than or equal to 1. Okay, so my cubic function shifted down 1, I know will look something like this on the left, and then it'll go up to the right. When x is equal to 1, we will have a hole. Okay, so that is a really badly drawn cubic function. Let me just try and make that a little bit nicer. Not so much, but that's okay. All right, and then when x is greater than or equal to 1, our y values are 2. So that's what that looks like. Okay. Okay, we're going to show that f at x is discontinuous at x is equal to 1. Okay, so we're going to start by doing the limit, and this is easy for us to see and answer, but we are going to show. So we need to show our work and use good form. So these, I would expect to see all of this in your response. Okay, so the limit as x approaches 1 from the left of f at x is equal to 0. The limit as x approaches 1 from the right of f at x is equal to 2. And since the limit as x approaches 1 from the left of our function is not equal to the limit as x approaches 1 from the right of our function, then the limit as x approaches 1 of our function does not exist. Therefore, it is, I'm running out of room here, discontinuous at x is equal to 1. So I would expect to see this, 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 and then your final answer. Okay, so all of those pieces. So just keep that in mind. Okay, so for question C, we're going to show that is continuous at x is equal to 0. So the limit as x approaches 0 from the left of our function is equal to -1. The limit as x approaches 0 from the right of our function is equal to -1. The limit as x approaches 0 of f at x is equal to -1 and exists. Okay, so we've shown the limit exists. Great. The second thing we need to do is take a look at our function at 0. And our function at 0 is equal to -1. So that's the second thing that we need to take a look at. And then we need to state that the limit as x approaches 0 of our function is equal to the function at evaluated at 0. So because all of these three things are true, therefore f at x is continuous at x equals 0. So note that this function itself is not continuous, but the function is continuous at x equals 0, so at a point. Okay, and that's it for today.